The failure may already be underway before anyone opens the adhesive. The part looks clean, the surface looks ready, the material has been qualified, the process has been used before. Everything appears to be under control. Then days, weeks, or months later, the bond fails. A coating lifts, an encapsulant separates, a component shifts. A joint that looked perfectly acceptable in production does not survive the real world. And when that happens, the adhesive usually gets the blame. But what if the adhesive did exactly what it was supposed to do? What if the real problem was something no one could see? Welcome, or hopefully welcome back to Reliability Matters, a podcast for the electronics assembly industry. Today we're talking about adhesion and why getting something to stick reliably is far more complex than simply choosing the right adhesive. In electronics manufacturing, adhesives are asked to do a lot. They may provide mechanical support, environmental protection, thermal conductivity, electrical conductivity, strain relief, or long-term stability in harsh operating environments. But even the best adhesive can fail if the surface is contaminated, if the process is not controlled, or if the surface changes before the adhesive is applied. My guest today is David Dworak, material scientist at Dymax. David recently wrote an article for Circuits Assembly magazine titled The Principles of Adhesion, Understanding Adhesive Chemistry, Application and Surface Science for Optimal Bonding Performance. We'll discuss adhesive chemistry, surface energy, contact angle measurement, plasma treatment, contamination, process windows, and why surface readiness may be one of the most overlooked factors in bonding reliability. And it all begins right now. Stick around.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Hey, David, welcome to the show. I'm excited to have this conversation today.
So am I. Thanks for having me.
You and I were talking off air about our respective industries. I'm in the cleaning world. You're in the adhesive type world. And your industry is to get things to stick to boards that either have or have not been cleaned. And we live in a world of no clean flux, which a lot of manufacturers mentally interpret as don't clean flux. And which may or may not be the case. You know, it may or may not be an accurate description. But when the bond fails or when the coating separates or whatever, as I mentioned in the intro, I don't get the blame. You get the blame. It's great.
I do.
Right? You do. Yes, exactly. Yep. So, you know, it's so funny because every industry thinks they're the blame of everything. When I talk to printing people, they say, you know, everything begins at the print. And that may be accurate, but the placement people go, you know, everything depends on the placement. Everything depends on the AOI. Everything depends on cleaning. Everything depends on the coating. So we all are, you know, falling on our sword, taking responsibility for the future of reliability of electronics, and we think it's all on us, but it really is a concert. It really is all of us in concert.
Yeah.
And what happens before it gets to your customers will determine whether you get the blame or not. And, you know, it's just the way the electronics manufacturing world works.
It is. Yeah.
Also, congratulations. This is your first podcast interview. So
it is my first podcast interview. So, yes.
So
excited.
Check that off your list. You could stamp the passport.
Done.
I know it's not your first time in front of a camera talking about this geeky stuff that we're going to talk about.
It is not,
because I've watched a few of your interviews, like at trade shows and things like that. And you do write about the subject as you did in that Circuits Assembly article. So you're a great person to have on the show.
Well,
Let's start with this. When a bond fails, is the adhesive usually? I kind of led into this question, so I'm just repeating a statement that I already made. When a bond fails, it's the adhesive that's blamed first, even when the root cause may actually be the surface, the process, or the timing. Why do you think that is?
You're right. The adhesive absolutely gets blamed first. Yeah, and why wouldn't it? what they were designed to do, hold two parts together. And it's what you and your design team, selected after reviewing dozens of technical data sheets, and you had discussions and compared properties, and you ended on this adhesive, and you put your trust into this adhesive, and you cure it, you apply it, and it fails. So we'll absolutely get the blame, because that is what you hope it's going to do on that part. So yes,
Yeah.
finger gets pointed at that.
When I speak at conferences on the subject of cleaning, one of the anecdotes that I love to point out is when I was much younger, probably in high school, and I had my first car. This was in the 70s. There was a painting company, and I think they're still around, called Earl Scheib. I don't know
Earl
if
Scheib,
you've
yeah.
heard of them.
I heard of them, yeah.
The owner, Earl Scheib, was famous for running originally newspaper ads and then eventually television commercials, where in his distinct voice he would say, "I'm Earl Scheib. I'll paint any car for $99.95." And that's pretty much how he sounded, because I play that clip in my presentations. And now think about it. He'll take an entire car and paint it for $100. Now the newspaper ads were $29.95. But I guess television ads are more expensive, so $100. And then I would joke that, if you have buyer's remorse and you determine that you don't like the color, don't worry, it's all going to peel off in about 6 months. And then I show an image of a car with sheets of paint off of it,
falling off, yeah.
Because for $100, they'll paint the car. They'll take the spray and they'll apply it to the car. No surface prep, no cleaning, no sanding, no primer, and it sticks to the dirt, and of course the dirt eventually, comes off. It's not, the dirt's not bonded. So the same applies to any type of adhesive process, whether it's painting a car, painting a room, or gluing two things together. We assume the surface is bond ready, and a lot of times they're not.
And it's assumption made by a lot of people. Yes.
Right. And when we consider circuit assemblies and how many processes the manufacturing processes, put the assembly through, from board fabrication, which I don't know if you've ever been to a board fabrication shop. It's a metal plating shop. It's a toxic, dirty from that standpoint process. And they clean it, but they don't clean it that well. And then it goes to the assembly house, where it sits on a shelf for a few months, maybe sealed, maybe not. Then it goes through a printing process. Then it goes through a pick and place process, and then it goes through other processes. And it's going through a variety of conveyors. It's being handled by humans, with or without gloves. And even with gloves, I can't tell you how many times I've seen people, we have to handle boards with gloves. And when they're done handling boards with gloves, they put the gloves in their dirty little ESG smock pockets, and then they pull them out again. Imagine if your surgeon did that. Right.
Yeah.
Right.
I know.
And, I always tell people, if you don't put fresh gloves on every time you touch a board like a doctor would when they touch a patient, just handle the boards with your hands. Because when you handle boards with your hands, you tend to hold it by the corners because you're very aware. You don't want your skin oils to get on it.
Right.
But when you handle them with gloves, you're manhandling the board, and then you're reusing the gloves. So anyway, these are all examples between multiple processes in multiple countries over a long period of time. These boards are picking up contaminants. Even if the flux is not applied to the board, theoretically, the board still has contaminants on it. So,
of course,
and all of that is underneath your stuff, right? So, that's definitely an issue. In electronics manufacturing, adhesives are used for far more than simply sticking two surfaces together. What are some of the common roles adhesives play in electronic assemblies?
Yeah, I mean, you're right. You hear the word adhesive, and your mind just kind of defaults into sticking two surfaces together. And
glue.
And yes, and the other applications of adhesives in electronic assemblies are not bonding two surfaces together, but they still do rely on the principles of adhesion to function properly. Like, for example, a conformal coating applied to a printed circuit board it's not bonding anything together, but it does need to, wet the surface of the circuit board completely and be properly cured to perform as designed. And encapsulants, same idea. They're not bonding anything together, but they need, to protect that circuit board from, shock, tampering, moisture, chemicals, etc. And those encapsulants need to bond well to various materials that are found on circuit boards, and it needs to stay put. You dispense it, it needs to stay, it doesn't need to flow. So other materials like staking materials, edge bonders, thermal interface materials, these all rely on being able to wet the surface and provide that robust bond. So yeah, there's many more applications beyond just adhesives on a printed circuit board.
Let's talk about adhesive chemistry for a moment. What are some of the key differences between acrylics, epoxies, silicones, UV curable adhesives, and two-part systems? There's a lot of choice here.
Yeah. Honestly, that question's a podcast in and of itself to kind of break down all of that.
All right, you're listening to part 1 of 10 of my interview with David.
Happy to do part 2 here about getting into the nitty-gritty about that topic. But let's talk about key differences. Let's talk about their method of cure. Some acrylics, some epoxies are 2-component systems. Silicones often will rely on a condensation cure where atmospheric moisture is required to initiate the cure. UV curable adhesives, those are going to utilize UV light to rapidly cure. So, cure methods are going to be different. Chemistry, of course, is going to be different. Acrylics, those are going to be used for more structural applications. Epoxies are used where maximum strength, stiffness, durability, chemical resistivity are required. Silicones are used where the adhesive might see some vibration or need some flexibility or need some permeability or can survive, thermal expansion of substrates, and they can kind of support those changes, in those dimensional changes.
Yeah, I see. I would think if you have a flex circuit that can bend a little bit, like maybe in a wearable that needs to be coated, you're not going to use an acrylic because it's going to go snap, when it bends.
Yeah, and that's where kind of, again, the chemistry gets interesting because acrylics can be, some can be structural, some can be flexible. Same for epoxies. Some can be flexible, some can be rigid and very durable. So, the polymer chemists can get really creative in how they, design these adhesives and getting down into the, molecular architecture of polymers and the oligomers that go into these systems. It's fascinating. So, like I said, part 2 possibly.
There you go.
Podcast here for you.
Audience, stay tuned. More coming.
Right. So, and UV curables too. Like those can be acrylic, epoxy, silicone, 2-part systems, acrylic, epoxy, silicones. And their advantage is they can be used like a 2-part. They can be used in areas where there's opaque substrates. And I'm comparing these to like a UV curable system where, if that adhesive can't see light, how can we get this adhesive to cure? Well, let's mix it together. We'll put it in this area here and let it cure. And that's an advantage. And you can apply it there. You can apply it in a thicker application than you normally would. The downside, of course, is now you have to wait for this adhesive to cure.
Right.
Your units per hour are going to be lower. Your production times are going to have to wait before you can move to the next step. So
everything has pros and cons, right?
Exactly.
There's a price to pay for everything.
Exactly right.
How much can chemistry compensate for, let's call it, less than ideal surfaces? Let's assume, just hypothetically, that someone doesn't want to clean, but they still want to coat or use an adhesive for some process. Are there, or can a better, in air quotes, a better adhesive overcome a poor surface?
So in the adhesive industry, there's a saying: you're only as good as the surface you bond.
Right.
Okay. And you kind of mentioned this earlier, where there's contaminants and dirt on the surface, and
I'll paint
Yeah,
any
your
car for $99.95.
exactly. You better clean it first, that's for sure. So, but like you were saying, if your substrate has dirt or a fine layer of grease or oil on it, and you don't clean the surface to remove it, well, you're now bonding to that grease. And I'm not familiar with any grease bonders that are out there on the market. So no, like a better adhesive can't understand, or excuse me, can't overcome a porous surface.
Right.
And we're going to get into talking about adhesives and surface chemistry. We're going to get into like surface energy and how to wet material, or how the adhesive wets the surface. And yeah, there's some other sayings in the adhesive business, such as the surface tension of your adhesive needs to be lower than the surface energy of your substrate in order for proper wetting to occur. We can get into more details about that. And when it comes to wetting, you can't force an adhesive to wet a surface. You can't force the adhesive to wet the surface.
My layman description of wetting would be, it's kind of like, I know when it's not wetting. So I don't know if this is an accurate description, but if you put a drop of water on, say you apply Rain-X to a windshield, and or you wax your car, better example, you wax your car, and then you put a drop of water on the hood, it beads up, right? And if the car did not have wax on it or some type of moisture repellent on it, and you put a drop of water in the car, it wets out. It spreads out to a very thin layer. Is
Correct.
that an example of wetting in this context?
It is, yes. That is, a key component. That's kind of one of the pillars in the paper there, the three pillars: the adhesive, the process control, and the substrate surface energy. And yes, the wetting comes into the substrate surface energy part.
Right.
And right, so for an adhesive to bond effectively, like you said, it must spread out on the surface and make intimate contact with it. And that is what wetting is. And the surface energy of the substrate plays a massive role in that.
And describe
And
what surface energy means for those who
yeah,
aren't familiar. I hear the term all the time, and I know that surface energy is important, but I'm not sure what the unit of measurement is when it comes to surface of energy. So or surface energy. So fill me in, fill my audience in a little bit on the background of that.
yeah, right. And you're going to hear surface energy a lot when you talk to adhesive chemists about bonding and applications and substrates. So yes, and surface energy, the definition is the energy required to make a new surface area. Okay, so for solids, it's the energy needed to break intermolecular bonds and expose a new surface area, new surface atoms, new surface molecules. So take metal, for example. It's a tough, resilient material whose atoms are held together by a sea of moving electrons in an organized lattice structure. This material is solid. It does not want to break apart easily. It's held
So that
together
would have
very
a high surface energy?
Yes. So
Yeah.
it takes a lot of energy to disrupt that structure and create a new surface area.
Yeah.
And yes, you're right. That's a high surface energy. And you contrast that to something like polypropylene. It's kind of a soft plastic whose composition is not a tight, rigid lattice structure. It's more polymer chains that are tangled and associated with each other through chemical forces. And the forces holding these chains together, they're weak. And this material requires much less energy to kind of break apart and create a new surface area. But to really get an idea of surface energy, like let's talk about exactly that, like its surface. Okay. So going back to the aluminum and polypropylene, if you have a cube of each of these materials, and now I want you to look in the center of this cube. And every molecule is surrounded by neighboring molecules inside this cube, and they push and pull on each other in all directions, and there's with molecular interactions, and they're all balanced. You pull this way, you get to push that way, and everything's just in harmony when you're in the bulk of the material. So everything's zero.
Center of the cube.
Center of the cube. Everything's zero. Everything's kind of equals and balances out. Everyone's happy. But now let's look at the surface. It's a very different environment than inside. So now you're on the surface. And let's look at polypropylene again, that soft plastic. It, again, consists of long, very stable, symmetric, non-polar hydrocarbon chains. Everything's stable. Everything's happy. Surface molecules are happy. There's no free electrons running around. There's no chemical groups on the surface like hydroxyl or carbonyl groups. It's just carbon and hydrogen. They're fine. There's no energy on the surface. It's not very active. This is a low surface energy material because there's not much going on the surface. So if I put a drop of water on that surface, that water's looking around for something to interact with. And there's nothing. It's just a hydrocarbon chain. So it's going to stay a water droplet. It's happy that way.
Yeah.
So it's not going to spread out. Now you look at metal, it's a completely different story. Like you said, they have very high surface energy because the atoms that are near the surface that normally in the bulk have something above it to balance it out. Well, now they don't. They have air. And those atoms are looking for something to bond with. They're in a higher energy state. They're hungry. They want to bond with something to reduce their energy to a lower state. So when you put a drop of water on that surface wants nothing more than to interact with that drop of water. So it's going to pull it in. It's going to disrupt the water's own internal forces that are holding it together. It's strong enough to then spread that water drops down on the surface of the metal and wet it completely. So that's
so we want assembly surfaces to have a high surface energy, so that they can break down molecularly the adhesive material or the coating material, whatever material we're putting on top of it, paint, in the case of Earl Scheib. It's a battle of wills, so to speak, where we want the target to be super strong, super powerful, have a high surface energy, so that the invading material that lies on top of it, it can break it down. If we have a low surface energy, I'm talking as a layman here, so I'm working this out in my head. So if we have a low surface energy, then we have a weak opponent, and the invading material that goes on top of it is going to win. It's not going to be broken down. It's going to remain as a water drop in the previous example.
Exactly. Yeah. You need to overcome those internal cohesive forces in the adhesive, in whatever you put on your surface. Exactly.
Are there adhesives or other things that stick, whether it's coating or adhesives? I'll just use the generically adhesives. Are there adhesives that are better at working with lower surface energy targets than others, or does the rule apply across the board that you really need a high surface energy target?
You do need a high surface energy target. Okay. Yeah.
There's no cheat. There's no cheat.
Well, I mean, there's ways to cheat. So that's where surface prep comes into play.
But we're cheating by addressing the surface energy of the target. There's no material that, Dymax and all the other companies don't have this special material that can stick to anything. No matter the surface energy, the material compensates for that. It's really more prep on the target than selecting a quote unquote stronger adhesive.
Right.
Yeah.
Right. Yeah. There's no universal. If you find one, let me know.
Well, yeah, exactly. Yeah. Well, I don't want people to find one because they won't want to clean, right?
That's true. You're right.
So if you find one, keep it a secret. Another phrase that we talk about in this world is contact angle. How does contact angle measurement help manufacturers move beyond visual inspection and better understand whether a surface is actually ready for bonding? So first, let's talk about what contact angle measurement is.
Yeah, so I'll kind of go back into wetting because it kind of relates contact angle and wetting, and that's where you need the adhesive to wet and make intimate contact with the surface. But getting into contact angle, there's this question of, what is the surface energy of my substrate? Like, is it high, low, is it medium? What is it? And there's, how do we get an idea of this value? And there's numerous tables and charts out there with values of materials, but maybe you're using a very, maybe a new grade of nylon, a very specific grade of nylon, and it's not on this chart, and you don't know. And you want to know what surface energy is, but there's no tool that you would put on the surface and it'll give you a surface energy reading.
Right.
That doesn't exist.
You can't scan it. You can't take a picture of it and it tells you.
You cannot. No.
Right.
So you need to use other measurements to help you infer that value. And a contact angle is the method that you do to get an idea of your surface energy. And what you want to do is you measure the contact angle of a drop of water on the surface of your substrate, and that'll give you a good indication of the surface energy and will help you predict if your adhesive will spray. So everyone's familiar with Teflon, so well known for being a very difficult to bond substrate. And again, if you look at the surface, everything is stable. There's no push or pull, or the Teflon chlorine or the carbon and fluorine is good. And
so Teflon would be a very low surface energy material.
Exactly. Very similar to polypropylene. Not much for those water molecules or adhesive to interact with because the surface is so stable. It's fine. And you put a drop of water on and it will bead up. And when you measure the contact angle of a water droplet, this will give you an indication of the surface energy.
And that's an optical measurement, right? It's an optical measurement.
Yes.
Is this device? What's the name of the device? It has a funny name.
Goniometer is the name.
Goniometer. That name never sticks with me. Yeah, I must have very low surface energy because that won't stick with me. But we're going to take this metaphor as far as it can go. So that device drops a droplet of water onto the target surface and then optically measures basically whether it's spread out or beading, or it measures the angle of the edge of the droplet, I assume.
Correct.
Okay.
And if you've got a water, a bead, and you measure and it's over 90 degrees, well, that's very hydrophobic and you're going to get poor wetting. And then as that droplet spreads out, that contact angle is going to get lower.
Way lower, yeah.
So a lower contact angle is good because that's a higher surface energy. And we want high surface energy target surfaces with a low contact angle. That's nirvana. That would be great. Yes.
Yeah.
That'd be ideal.
I think it's important for everyone to consider the laminate material, the FR4, whatever, the laminate material that boards are made out of, may have a relatively high surface energy. So people may think, well, this is totally bondable. There's no reason things won't stick. It's got a high surface energy. What we need to check is what's the surface energy after we put a bunch of low surface energy contaminants on top of it, right?
Exactly.
Because it's not so much the material below, although that does matter. It's what's between the material below and the adhesive above, right? It's an Oreo, so to speak. That white stuff in the middle that tastes so good may have a very low surface energy. And
great analogy, that's why when you purchase an adhesive and you look in the instructions on how to use it, take a guess at what the first step is. What they always tell you to do.
Clean.
You buy an adhesive, even something from hardware store.
Yep. Clean, dry surface.
Clean the surface with IPA or isopropyl alcohol, water.
Yeah.
I wonder why they have you do that.
Even cans of paint for your house, for the walls. Say, they expect the surface to be clean and dry. Both.
Prep your surface.
No
Prep
moisture,
your surface.
no contaminants.
Right.
Why can a surface that looks clean visually still be a poor surface for bonding?
So you can, going back to Teflon and polypropylene, you can clean that all you want. You can IPA and soap and water, but you're still going to have difficulty bonding with it because of its low surface energy. All right, but maybe you cleaned. Let's take another substrate. Maybe you had some polycarbonate that you're bonding, and you cleaned it really well with some industrial soap and water, and you're still getting poor performance. Well, there could be a surfactant residue in the surface which can disrupt bonding, or maybe you cleaned your parts and to be bonded and allowed them to sit in a staging area, and over on the other side of the room there's an aerosol spray system, and the current of the room, the air draft is blowing over, and now it's depositing onto what you thought was an already cleaned part. Well, now you've got a thin layer of whatever was being sprayed is settling onto your parts, and you now have a contaminant that you didn't know about. But let's even in the metals. Let's say you polished and cleaned your aluminum to a perfect shine, and you're good. But you let it sit for several days before bonding. Well, this gives the aluminum time to react with the moisture in the air and form an oxide layer, and those oxide layers sometimes don't adhere very well to the base metal itself. So now you're bonding to an oxide layer and not the metal. So cleaning is a very important step in surface prep. But surface energy, contaminants, surface chemistry, all that stuff needs to be considered. Again, it's an assumption that we talked about earlier where surface is fine. You just got it in, cut the box open, use as received. It might not be as clean as you think.
Yeah, and I think a good follow-on to that would be, when we say clean, what do we mean? Optically clean, visually clean, or ionically clean? Those are two different things, because no clean flux, one of its claims to fame is that it leaves no visible residue. And when it's reflowed properly and all the peak reflow temperatures are hit for the right amount of time, and the bad actors or activators and all that are volatilized thoroughly, it generally leaves no visual residue. It does not leave no residue. It leaves no visual residue. So you look even under 32x, you're looking down into the scope and it looks great. You would eat it. You would eat a meal off it.
Right.
But does that mean it's clean? No. Some of my friends and colleagues at Foresight, which is a contamination laboratory in Kokomo, Indiana, specifically for the electronics industry, published some papers that talked about the certain type of black foam that one would put in an ESD box to ship a board in. And so the board, the foam is nice and soft, like you would expect, and it could be routed out to, surround the board and protect it in shipping. They've detected residues from that foam that kind of break down over time and temperature and adhere to the board and create electrochemical migration issues later, or possibly bonding issues later too. But in this context, it was electrochemical migration. And I'll tell you, if it's causing ECM, it's also a surface energy issue too. So we can't rely on our definition of cleanliness with the microscope. There are surface insulation resistance, resistivity of solvent extract tests, or all sorts of tests that are designed for that purpose that can detect invisible residues, and microscopes are not it. The article that you wrote discusses surface treatments like IPA, wiping, and plasma treatment. What does each method do well, and where can they fall short? Everything in our world is pros and cons, so walk me through that.
If only there was only just all pros, that would be
all
ideal.
pros. Well, then we would be greeters at Walmart or something. We wouldn't have anything to do.
But both IPA and plasma treatment, they're surface preparation methods. Completely different principles. IPA is a white chemical cleanup. Plasma treatment is surface activation, or like a surface modification step. And the isopropyl alcohol it's great to remove surface contaminants. Again, we talked about dirt, grease, fingerprints, oil like that. It's a cheap, mild solvent. It can be put into just about any processing line and can be used on pretty much all metals and plastics without you having to worry about it marring the surface or causing any issues like that. So in that aspect, it's very nice. But things you need to consider with IPA is its purity. There's 70, 80, 90% diluted with water. Water is not always clean. There could be impurities there.
70% is rubbing alcohol. That's what a lot of people use. We use anhydrous alcohol, which is 99.9% moisture free.
Right.
That's pure alcohol.
But it is pure, but even the 99.9, there's that 0.1%.
Yeah,
what is
exactly.
that 1%? It's something. It's better than 70 for sure. But again, it's a source of possible.
Yeah, I think IPA is one of the worst solvents to use, but it's so readily available. It's omnipresent. It's ubiquitous. It's in every little pump bottle on every tech. If I owned a manufacturing company, I would throw away all those pump bottles because they're better solvents than IPA. But it's easy. It's not generally considered environmentally harmful. It evaporates quickly, so it hits and it does clean up many of the contaminants. Not all.
It does. Not all, but again,
but some it reacts with. Some it reacts with. If you use IPA to try and remove no clean flux, it turns those invisible residues white.
Okay. I didn't know that.
There it is. Yeah. Now it's still not ionic, or it may or may not be ionic, but it just basically makes them visible and very difficult to remove that white residue, short of reflowing the board. It's just a chemical reaction between some of the activators in the flux. But is it safe to say that IPA or other solvent type wipes, they don't modify the surface; they simply remove the barrier between the surface and the adhesive, where plasma treating actually modifies the surface, right? Is that correct? I view plasma treating, and I might have this completely wrong, but in my simple mind, I view it as slightly abrasing the surface, giving it more surface area to cling on to. Is that happening, or is it really more of a chemical reaction that's altering the surface energy of the target?
Yeah, it's more the latter there for that.
We're not sanding it down, in effect.
Sanding, maybe on the nanoscale, but maybe, but nothing like a grit blast or anything like that. Creating those nooks and crannies for a physical bond versus this plasma treatment, like you're talking about, which is physically modifying the surface chemically. Chemically modifying the surface. Yes.
So can plasma treating drastically affect surface energy, subtly affect surface energy? Can it make a difference? In other words, can you bond to Teflon if you plasma treat it? As an extreme example.
Yeah, that is an extreme example, and there's a handful of different type of plasma treats, just like there's different types of solvents to wipe your surfaces on. And can you plasma treat Teflon? Yes, you can. Does it increase the surface energy? Yes, but it's you got to apply vacuum. You have to do a certain type of plasma, and it's a more long, thorough, drawn-out process than kind of the traditional open-air plasma that you might be used to. That's out on a line where you just kind of zip in substrates back and forth.
Yeah, but in our world, since fortunately boards aren't, components aren't mounted to Teflon. So in our world with standard, fiberglass type materials, plasma treating has a pretty good effect, and that can even be open air, inline, not vacuum dependent plasma treating.
Right. And this is kind of where we were talking about cheating, a little bit on the surface. Yeah. How can you cheat and help you bond? And plasma treatment is one of the ways that you can cheat. And, plasma treatment, what we're doing is we're taking a gas, and in this case, kind of the method that we've been talking about, like compressed air, and you're passing it through this intense electric field. And this causes, gas molecules to become very excited and undergo chemical changes. And you create this highly reactive, like, pool of ions and free electrons, free radicals, excited state molecules. And you're blasting all of these components onto the surface on your substrate. And these highly energetic species chemically react with the surface, and now it's going to give your adhesive something to interact with. You're kind of like putting hooks of Velcro onto the surface now to give your adhesive something to grab onto and get that intermolecular association that you're looking to get to help improve adhesion and improve wetting. So yeah, you're giving a low surface energy material, you're increasing the surface area by making it more reactive, giving that water droplet or adhesive, oh, look, here's something I can look, and they attack and associate with that and get some better wetting. And plasma also has the bonus of you're kind of doing a little cleaning of the surface too. Those high energy particles, they're hitting those oils and greases, kind of breaking them down and volatilizing them off. So you get a nice clean surface as well. And it sounds awesome. Like, it sounds great, but as again, we've been talking about pros and cons. And the con with plasma treatment is this highly energized surface is not permanent. All right. The moment plasma treat is complete and it gets past that little blast of plasma, that surface is hungry for something to react with. And it's not going to wait for you to put your adhesive down for those species to look for something to react with. And that could be moisture in the air, maybe some air contaminants, something, anything. It's looking to us because you put your surface into a higher energy state. And, materials don't like to be in higher energy states. They want lower energy states. So with a plastic, like polypropylene, or even that Teflon that you just treated a little bit ago, those polymer chains are going to do whatever they can do to get out of that high energy state. And they'll twist and try to bury those high energy components, get them to react with something to not be in that state. And so you don't have a lot of time once you plasma treat to take advantage of that high energy surface. So you've got anywhere from minutes to hours to take advantage of your plasma treatment step.
Right.
And
treat and then bond, or treat and coat.
As soon as possible. Do not set them off in a staging area and let them sit there for 2 days and come back and think they're good to go. They're not. They've lost most
shelf life
of that surface energy that you put into there. Correct. Yeah.
For a manufacturer experiencing adhesion failures, where should the troubleshooting process begin, and what objective evidence should they be gathering?
Aside from pointing at the adhesive person and
they've already done that. That's on the list. Boom, done. Okay, they've already blamed David. No. All right.
A bond fails. Where do you go? What do you look at? How do you approach something like this? And there's a few avenues to take, and we can take them all. But let's look at the substrate first. Do you know the surface energy of your substrate? It might be on a chart again. Maybe you collected it. Are you able to answer the question, is the surface tension of my adhesive less than the surface energy of the substrate? Like, first of all, are you getting good wetting? That's kind of where we would start. And if you are, and everything looks good, and your contact angles, and you use your goniometer, and everything looks good, let's look for sources of contamination. We've been talking about sources of contamination that are even new to me, like the black foam, and you deposited something onto the substrate there. That's an interesting source that, again, people wouldn't normally look at. So, again, look around your production area. Are there sources of contamination? Is there someone spraying aerosol something down the way? Is there oil or grease on their substrates as received? Do that type of check. Look into that. Are you curing? So if that looks, then that's okay. Next thing to look at. Yes, now let's look at the adhesive. Surfaces are looking good. Let's look at the adhesive. Did you cure it properly? It's something that often, even though it seems so simple, that sometimes gets overlooked. Did you mix your 2K epoxy in the right ratio? Did you mix it enough? Did you give it enough time? Did you let it sit long enough before you moved on to the next step? Did you deliver enough UV dosage into your UV curable adhesive? Look at your cure methods. Are they what the manufacturer is suggesting that you do to get a properly cured adhesive to perform as designed on your application? There are analytical methods you can use to determine the degree of cure for some adhesives. So that's web podcast number 3, I think, for us now.
There we go. All right, it's a whole series now.
And you might find a way you're only curing your adhesive maybe 80 or 90%. Like that's enough to hold it together and move it around and give you good green strength. But in the end, when you finally put that assembly through your testing, that extra 10, 15, 20% cure, that's absolutely a massive amount of percent cure to be missing, and your adhesive is just going to fail.
Right. It might be enough to get it out into the shipping department, but once it's put into the real world with shock and vibration and other elements, it fails.
Yeah. But I want to go into also how the adhesive failed. That's also a very important factor to consider. So if the adhesive completely delaminated from one of the substrates, it just popped right off, then that is termed adhesive failure. And that suggests a surface energy or contamination or a wetting issue where the adhesive just doesn't want to bond to the substrate. And again, it just popped right off. There's no association there. So that's something you can look into there. If the adhesive tore apart and stayed on both substrates, that's termed cohesive failure. And this tells you the adhesive adheres well to both substrates, but the bulk polymer failed. And this could be due to maybe you over-cured or under-cured the adhesive, like we're talking about. Maybe it's 80% cured, enough to get it out the door and hold together, but under stress, it breaks apart. Also, the adhesive breaking here might be okay if the force that it broke at was above your required. That might be okay. I just want to say it's not the end of the world if that happens. Right. And then there's substrate failure, and that's where the adhesive was totally intact, but your substrate itself failed. And if that's the case, now you look into your substrate for possible sources of weak areas, micro cracks, voids, over treatment of maybe I don't know, just that's where you want to start focusing on your substrate. And there might be some design issues too that cause maybe that area is stressed out more because of the design of the component or whatever. There's a lot of areas that you can look into when it comes to substrate failure. So yeah, a lot of things to check out when a bond fails. Again, how it failed, contamination, the adhesive itself, a lot to focus on instead of just the adhesive.
Yeah. It's a successful adhesion process is really a partnership between the material supplier and the user, because each one has responsibilities to ensure a good bond. It's not just buy a can, apply it, everything is good. It's a two-part system.
Absolutely.
Talk about two-part bonding. It's really two-part adhesion in every case. Final question. What are some of the most common mistakes companies make when qualifying an adhesive for electronics applications?
Yeah, that's an interesting question. I would say comfort. One of the things we see a lot is just, we've always used this, so let's keep using it.
History.
It's just we're comfortable with this, so let's just go with it. Well, it's not working. Well, okay, that's because there's likely a better product.
But it used to work. but it used to work.
Yeah, exactly.
When we had back in the through-hole days, it used to work.
Right. And substrates change and everything, but it just certainly, it's again, we always hear, oh yeah, we had that adhesive on the bench, so we just tried it. Isn't it all the same?
Yeah.
Aren't all UV curables, aren't all epoxies the same? No, they're not. So yeah, it's comfort. Unfortunately, cost comes down to it as well. This one might perform a little bit better, but this one's a little bit cheaper. So, well, we've seen instances where, yeah, cost is a big factor. And I mean, in the adhesive world, you kind of get what you pay for,
Well, that's
so
the old saying, we can't afford to do it right, but we can afford to do it over.
Exactly. Right. And then just, maybe overlooking what you need that adhesive to do. You don't just need it to hold two things together. Maybe that application is going to bend or twist or drop or get exposed to shock and vibe. There's so many adhesives out there. Let's look. Let's see what's out there. Take the time to do it. I know time is of the essence always, and oftentimes, again, you're selecting either what someone knows, maybe someone recommended something, or you're just familiar with a certain type of chemistry, or you're pigeonholed into, we only have heat cure systems, so that's all I can use. But you might have to go outside your comfort zone here. You might have to invest in other cure equipment or whatever you need to make the adhesive work for your application. So yeah, it's often a lot of those components are considered there.
Excellent. Well, to my audience that would like to get more information on Dymax and their stable of products, and if they'd like to read the article written by David, the links to both Dymax and the article will be in the show notes. If you're watching this on YouTube, right down here below me, it says see more. Click that, and that will take you to the show notes, and you'll get the URLs there. If you're listening to this on your favorite podcast app, then go to your podcast app, look at the show notes, and that information will be there as well. David, congratulations. Your first podcast done. It's in the can.
Good.
Yeah.
Thank you. I appreciate that. No, this was a lot of fun.
Yeah, great job. I really appreciate your expertise and willingness to take the last hour or so and share it with me and my audience. I think it is such an important topic when it comes to reliability, and it's a space I'm comfortable with and very familiar with, because we should be in best practices the precursor to your process. So we're neighbors, and it's so vital, particularly today in the era of miniaturization and IoT, where we're throwing electronics out into the harsh, cruel world that we didn't formally do before, and so much is expected in terms of reliability today. With electronics being as ubiquitous as they are now, we're seeing all sorts of failures that we didn't see before, or at least the scale of the failures that we've never seen before. And the tolerance for residues, the tolerance for failure, the tolerance for all sorts of things is much lower today than it was just a few years ago. In fact, it's probably lower now than it was before we started talking an hour ago. So
you're right.
It's changing so rapidly. So thanks for doing what you do. Continued success. Thank your team for generously sharing you with me and my audience. I appreciate it. I know my audience will as well.
Oh, that's great. No, again, this was wonderful. And again, thanks for the time. And this was fun. Thanks.
I agree. Before I wrap up, here are some final thoughts. As we heard today, adhesion is not simply a matter of choosing the right adhesive. It's a system. The adhesive, the surface, the process, and the timing all have to work together. A surface can look clean and still be a poor surface for bonding. Contamination, oxidation, residue handling, humidity, and even the amount of time between surface preparation and adhesive application can all affect the final result. And when the bond fails, it's easy to blame the adhesive, even when the real issue may have started long before the adhesive was ever applied. One of the most important takeaways from David's article and our conversation is the value of objective evidence. Contact angle measurement gives manufacturers a practical way to evaluate surface readiness rather than relying on assumptions or visual inspection alone. In electronics manufacturing, reliability is rarely created by one big decision. It's built through a series of controlled, measurable, repeatable process steps. Adhesion is no different. My thanks to David Dworak for joining me today and helping us better understand the science behind adhesion, surface energy, and bonding reliability. Now, that's a wrap on another episode of Reliability Matters. Thanks for being here, whether you listened on your favorite podcast app or watched on YouTube. I really appreciate you being here. If you haven't already, hit that subscribe button so you don't miss future episodes. On YouTube, give it a thumbs up and subscribe. Those 2 simple clicks really help us expand our reach. And a big thanks to PCB Chat from the Printed Circuit Engineering Association at PCBchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Got a question or an idea for a future episode? Of course, we'd love to hear from you. Visit reliabilitymatterspodcast.com. Want to learn more about the podcast? Head over to reliabilitymatterspodcast.com. Thanks again for being here. Until next time, keep learning, keep doing it right, and remember, reliability matters. I'll see you again soon.
Thanks for listening to the Reliability Matters podcast. Join us on the 2nd and 4th Tuesday of each month for new episodes of Reliability Matters.